Hello everyone. In this video, we'll discuss a very important topic from coordination chemistry, that is crystal field theory. Now, in order to understand crystal field theory, we have to know some basic things, that is what are coordination compounds. Coordination compounds. Now, coordination compounds are those compounds which contain those metals with d electrons. What is this d electrons? The electrons that are present in d orbitals. Now, how many d orbitals are present? We have 5 d orbitals, right? What are these? They are dx square minus y square, dz square, dxy, dyz, and dzx. These two that are in the beginning, dx square minus y square and dz square, they lie along the axis. The remaining three, that is dxy, dyz, and dzx, they lie in between the axes. Now, what are these axis thing that we are talking about? See, if we draw a three-dimensional structure and represent my dz square orbital, this is my z-axis, this is my positive, and this is my negative charge. Okay, so this dz square orbital is entirely present along the z-axis. Similarly, if we see dxy orbital, we'll see that if this is my x-axis and this is my y-axis, it is present in between this x and y-axis. Hence, this is dxy orbital. Okay. Now, in the next thing we have to know here is the metal and ligand interactions. Now, in a very perfect environment, which is not possible in nature, the metal ligand interactions will be equal. It must be equal, but it doesn't happen, right? What happens is that metal and ligand, they interact unequally. Because they interact unequally, the metal orbitals, which I mean d orbitals, also interact unequally, and therefore the degree of instability that happens is different. Why this is becoming unstable? Because see, initially when there was no ligand present, all the metal orbitals were degenerate, that is, they were of equal energy. The term degenerate means equal energy. But when the ligand keeps on approaching, this degeneracy gets disturbed. Okay, it is getting disturbed due to incoming ligands. Now, what happens is initially the metals and ligands, they are arranged in a spherical manner, okay, like this. These are my ligands. And this is my metal cation, okay. But in this configuration, there is two types of forces that comes into play. One is an attractive force and another is a repulsive force. What is this attractive force that is coming? See, there is attraction between the metal cation and the ligand, which contains either negative charge or a lone pair, right? We know that positive and that if anything that is positively charged will obviously attract electrons or something that is negatively charged. So this attractive force is coming into play here. Similarly, there is another repulsive force that is happening between the repulsive force that is happening between the d electrons and the lone pairs or electrons over ligands, right? Now what happens is at one point of time, this repulsive force becomes greater than this attractive force, okay? And this entire configuration that we're seeing here is disturbed. In this disturbed configuration, what we see is splitting of d orbitals, which leads to loss of, which leads to loss of degeneracy. Okay. See, if we have 5 d orbitals, 1, 2, 3, 4, and 5. Okay. Now, initially, it will get destabilized, that is, it will gain some energy. Now, what is happening is splitting occurs. Okay. Now, when splitting is happening, if you remember it correctly, then I told you that there are 2 orbitals that lie along the axis and 3 orbitals that lie in between the axis. Now, the ligands, they have a tendency to approach along the axis. So which are those orbitals which will interact more with ligands? Obviously, the one which lie along the axis, that is my dx square minus y square and dz square. These are the one interacting more with ligands, right? So if they're interacting more with ligands, then they will get destabilized more. That is, they will gain energy. So what is happening is they are getting destabilized, and this is my dx square minus y square dz square. Similarly here, in order to preserve the equilibrium condition, the remaining 3 orbitals will get stabilized. That is, these are my dxy, dyz, and dzx, okay? And this is my barycenter. That is the point of equilibrium, okay? Now you may ask me that whether the extent of this splitting, if it is equal. Now, if you mean by that, then see, we have 5 orbitals here. 1, 2, 3, 4, and 5, right? Now, when it is splitting, and this is my barycenter, this is destabilized by plus 6 dqo, okay? And this is stabilized by minus 4 dqo. Now, what is this dqo? dqo is the energy difference from barycenter. Okay. Now, why this is plus and this is minus? Because obviously this is getting destabilized. So it is gaining energy. That is why this plus sign is coming. Here it is getting stabilized. That is, potential energy is decreasing. Therefore, this minus sign is coming. See, overall, I said that an equilibrium will be maintained. We can prove it like this. See, we have 2 orbitals here with 6 dqo energy, right? So 2 into 6 dqo. Similarly, we have 3 orbitals with minus 4 dqo energy each. So this is plus 12 and this is minus 12 dqo. So obviously the net energy is 0, right? So there is conservation of energy, right? As we have learned, as it happens with almost all systems. So the next question you may ask me is that whether this type of splitting is only seen in octahedral complexes? No, actually no, because this type of splitting is also seen in tetrahedral complexes. tetrahedral complexes. See, in tetrahedral complexes, what happens is, let's draw a diagram for better understanding. This is my x-axis, y-axis, and z-axis. Okay, x, y, and z. Now the ligands will also be along this axis, x square minus y square and dz square orbitals. They will be along the axis, and the rest of the orbitals will be in between the axis. But in case of tetrahedral complexes, the ligands, they don't approach along the axis. They approach in between the axis. That is, if we utilize some common sense, it is very much visible that the ligands that interact more in case of tetrahedral complexes with ligands are the dxy, dyz, and dzx orbitals, right? These are the ones. And the ligands occupy space like this, L, 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 and L. Okay. So see, none of them are occupying any position along the axis, only between the axis, right? So in this case, the splitting will happen like this. 1, 2, 3, 1, 2, 3, 4, and 5. Okay. Now this is getting a little bit destabilized. 1, 2, 3, 4, 1, 2, 3, 4, and 5. Okay. This is my barycenter. Barycenter. Now, because this is getting more destabilized, the dxy, yz, and dzx, this will get stabilized, right? What are these? Dxy, x square minus y square and dz square. This is dxy, dyz, and dzx, right? This is stabilized by minus 6 dq t, not dq o here. Okay, the o in the previous case stood for octahedral, and t denotes tetrahedral. But the thing is, delta value is same, that is the energy difference from the barycenter or the point of equilibrium, right? So, and this is plus 4 dqt. Now, if we equate the same, we'll get 0. That net energy difference will be 0. Okay. So what is happening here is that because of the ligands approaching from a different way, the entire configuration is changing, right? Because these 3 orbitals, these 3 are getting stabilized and these 2 are getting destabilized. Sorry, these 2 are getting destabilized, these 3 are getting destabilized, and these 2 are getting stabilized. Now you may ask me that if the extent of splitting, crystal field splitting, if it is same for octahedral and tetrahedral, the answer is no. Why? Because see, in octahedral, we had 6 ligands. And in tetrahedral, we have 4 ligands. So if we compare, it is 2/3 of its value. Similarly, I told you that in case of octahedral, the ligands approach along the axis. In case of octahedral, right? In case of tetrahedral, ligands approach in between the axis. So for this purpose, for this only phenomena here, there is another reduction of 2/3 of value, okay, compared to octahedral. So the net result we'll see is that delta T value will be 4 by 9 times of delta 0. Okay, this is a very important relation we have to know. Okay, so this is like somehow of a very gist concept of crystal field theory, and a very foundational ones also, because if you don't understand this topic, we'll not be able to understand its applications. Okay, so let's go to the like the gist of the and like the entire summary of whatever we've learned in this video. At first, what we learned is that what are coordination complexes. Second are the orbitals. The third thing we saw is that how the metal ligand interaction is taking place. The next thing that we learned was that how the degeneracy is getting destroyed, and obviously splitting is taking place. The next thing that we learned is that how the splitting happens for tetrahedral complexes. And the last topic that we discussed was that how tetrahedral complexes interact with ligands and how it is different from the octahedral complex, and it is obviously less, the extent of splitting is obviously less than octahedral complexes, right? So this is what we'll conclude with this video. And I'll suggest that please go through this topic in your book, because otherwise you'll not be able to follow our remaining lectures. Thank you, and please take care.